in the 70s. But more recently, there's been a lot of seismic activity caused by technological activities. And probably the clearest, most dramatic example is shown in this slide from Bill Ellsworth, which plots the earthquake count in mid-continental US against time. And you see this hockey stick-like increase in red against the background rate that's existed for many years. But there's also been a lot of other, oh, yes, I forgot to mention that, yeah, so I think this is pretty well established that the increase is due to injection of waste fluid from hydraulic fracturing operations. But there's been a lot of other cases of fluid injection causing seismicity. One example is the recent case in Strasbourg, which I think caused suspension of the geothermal program. There's an older one from Basel and one in Switzerland. There's also been cases of seismicity caused by injection for carbon sequestration and disposal of liquid waste. So this has prompted many nice analyses of
Let's not do that.
effects of injection
Somebody
on seismicity, and at least one very nice field experiment by Guglielmi. I apologize if I mispronounced your name. And I think ultimately, though, these issues have to be solved by field experiments, but there's always uncertainties about the mechanical and hydrological structure, the history of the site, the stress state. And so I think that experiments, despite their limited size and timescales, can offer a lot of useful information. They're conducted under more controlled situations. And by comparing them to calculations, I think that can reveal more about the experiment and also some of the limitations and things that are left out of the particular calculation. So that's my point of view, and I'm going to go with it. And I will talk about 3 experiments, one by Scuderi, Colatini, and Marone. Actually, Chris suggested that I look at this, and Marco provided some helpful information about some of the parameters and a few details of the experiment. He also suggested that I look at the second paper on here, and again provided some useful information. The third paper I decided to look at all by myself, by Noel Passelgil. I'm actually taking a French class trying to improve my French, but I probably haven't improved it enough. Georgetic and Maria Ville. Corentin Noel also provided some helpful information. So I want to thank all those people. The first 2 are described in more detail in this recent paper. The third one is kind of still under construction and is being done mostly by Michaela Mercury. Okay, so we're going to use rate and state friction. Probably most people know about this, and maybe more than I do, but I'll go through it anyway for those who don't. So the canonical experiment is to take a block of rock and slide it over a frictional surface. And if this is sliding at a steady state velocity, which is one of the tenets of rate and state friction, that you do have a steady state velocity, and you suddenly increase that velocity, the friction coefficient jumps up as the log of the velocity ratio, the parameter A, and then it decays roughly exponentially over characteristic distance, d sub c, and eventually reaches a new steady state level that's characterized by the coefficient B. So those are the three parameters that enter. Yes, if B is greater than A, the new steady state level is below the old. This is velocity weakening. And if it's less than A, then it's velocity strengthening. So Andy Ruina and Jim Dietrich put this in equation form. This is the shear stress. A and B are typically about a few percent, and so usually much greater than the nominal coefficient of friction. Theta is a state variable which keeps track of the evolution of the surface and can be roughly correlated with the age of asperities. There are two that are used. There are some differences, but for the purposes here are maybe not so important. Okay, the main difference is that at very low velocities, the aging law, the state increases. For low velocities, the slip law does not. At steady state, theta is equal to the characteristic sliding distance dc over the steady state velocity, and you get this expression for the steady state shear stress, and you can see the dependence of A and B here. Now this is for constant normal stress. If you have a change in normal stress, then Linker and Dietrich, based on their experiments, proposed this form, and Richardson and Marone did some more work on this. So alpha is another parameter, and it predicts that if you have a sudden change in effective normal stress, you also get a sudden change in the state variable. Let's see if there's another thing on here. There are some issues about this, which I don't see come up, but Kilger et al. Have done some more elaborate experiments, which suggests that this is maybe not needs some modification. And there's an issue that Ranjith and Bryce have noted, that any law that predicts a sudden change in state with a sudden change in normal stress gives to an ill-posed solution, at least for slip between two dissimilar elastic surfaces. Yes, here it is. So yes, and Sridharan et al. Have also looked at this a bit, and I think they suggested that this form is reasonably described their experiments, and we're going to use that. Okay, so, but this is a place where probably more some attention needs to be paid to how what is the proper form of that. Okay, and then if you add a spring to the system, again, this was done by Andy Ruina, you find that when you have velocity strengthening, small perturbations from steady state decay exponentially. You have velocity weakening, and in addition, the spring stiffness is less than some critical value. The perturbations from steady sliding can grow exponentially. And one thing to note here is that the pore pressure, an increase in pore pressure increases K critical, and that is stabilizing, in contrast to the usual Coulomb formulation, where an increase in pressure decreases the effective normal stress and hence is destabilizing. If you write the equations for that, so this is the F equals ma. However, the acceleration term is approximated by this radiation damping, which prevents solutions from becoming completely unbounded. And you can well, you can just plug these into MATLAB or MathCAD and solve them. An example of what happens is shown here. If K is slightly less than K critical, you get slightly more than K critical, you get decaying oscillations. Slightly less, you get increasing oscillations. As K decreases, you begin to get these rapid slip spikes interspersed with times of very slow velocity. So sequence of earthquakes. The other thing that comes into the connection with fluid is the porosity equation. And Siegel and Rice proposed this form based on experiments of Chris. This epsilon is the magnitude of the effect. Now, the Sleep proposed an alternative form, and the form I've written here is from Paul and Jim. Yeah, I found it a little bit difficult to extract the form from Sleep's paper. But anyway, so these are different in the sense that the Sleep form depends on the state, and the Siegel-Rice form depends on the velocity. However, they're the same for steady state velocity, and they linearize to the same form, but there are differences between them. And I've looked at this a bit. This shows the change of the state variable. Yeah, I should say too that they're also similar for the velocity stepping tests and for normal stress jumps at constant velocity. But for the slide, hold, slide test, they're different. And the top graph shows the state variable, the bottom, the change in porosity normalized. You can see that there is some difference between them. The Sleep law turns out to be equivalent to the Siegel-Rice form with the Sleep equation with the slip law. And when you use those in a simulation, this is sort of arbitrary value of the spring stiffness. Here, it's the log of the velocity, porosity, pore pressure, and normalized stress. They look essentially the same on the left. However, if you blow up one of these, there is a difference. And for parameters corresponding to lab values of D and DC and the reference velocity, that's about 5.5 minutes. If you use values appropriate for the field, that's let's see, where is it? It's about 5.5 years. So the difference can be significant. And this simulation agrees, well, it's consistent with the observations of Proctor et al. Were recently, and one of their conclusions is that the change in pore pressure can cause a greater change in the shear stress than the rate and state effects. So the formulation of Siegel and Rice is based on the experiments that Chris did on quartz gouge. So this is another area that I think is amenable to further experimental analysis to decide, well, is that the best law to use or does it need some revision? Fluid flow, I'm not going to go into much and just skip to this equation. It employs the membrane approximation, which says that the flux of fluid is just proportional to the difference between the reservoir pressure and the pore pressure at the frictional surface, rather than being described by a diffusion equation. Paul Siegel, Alan Rubin, Bradley, and Jim Rice have looked at the difference between these two a bit. We've been trying to look at that a bit too. Yeah, there are some differences. but we're going to use this membrane approximation because it simplifies things quite a bit. What else we got? Yes, so we're finally to the experiments. This is the first one. It's in the double shear apparatus. So the gouge layers are confined here. And then this ram is advanced to shearly layers. This is done on carbonate bearing fault gouge. And the loading program is shown here. It's loaded to a steady state shear strength, and the load point is stopped, and so the sample relaxes. Then they increase the shear stress to 90 or 80% of the steady state level, creep for another hour, and then hold the shear stress level constant and begin injecting pore fluid. And they do that at two rates, megapascal per hour and 0.2 megapascal for 12 minutes. So they have the same average injection rate. And one of their main conclusions is that the fluid pressurization can trigger dynamic instability even in cases of rate strengthening friction. So we'll talk more about that in a second. The parameters, which you mostly get from the paper with some help from Marco. See what to say about this. The rate and state parameters here, A is greater than B, so it's velocity strengthening. So you should not see instabilities. The Linker-Dietrich parameter we didn't have, and so we just chose a value of 0.3, which, well, plausible. This shows again the simulation of the loading conditions. We find a drop from the end of the zero load point velocity segment to the 80% steady state level, which is a discrepancy with the experiments. I'm not sure exactly why that is. Everything is done here in non-dimensional parameters, but a time of 1371 corresponds to 60 minutes. And you can see that, well, this zero load point velocity is an hour, and then it creeps for another hour. This is their results. So the 90% is on the left, the 80% on the right, and the top row is the 0.2 megapascals per 12 minutes. The middle one is the megapascal per hour. So they start injection, they get basically steady increase in slip. So they call that bulk creep. And then there's an onset of tertiary creep, which they identify, and then a rapid upturn in the slip, and also the velocity. So they do see a unstable behavior, even though the material behavior is velocity strengthening. This shows the calculations. The red is the log of the velocity over the reference velocity. The blue is the pore pressure increase. The number at the top is where the onset of tertiary creep is identified in the experiment. And the horizontal line here shows the pore pressure at that level. The lower line shows the velocity that they identify in the creeping segment. And yeah, the well, the simulation actually has no bulk creep in it, but the value of the slip is not too different from that. So you see again that after this identification of tertiary creep, you do get a rapid upswing in the velocity. And here it's big. So the log of velocity ratio is like 8. And then there's some other stuff that happens up here, which I think is not relevant once this gets so high. And the prediction is not so bad. I mean, it follows the onset of tertiary creep by a bit, which you'd expect. A bit here. Here it's a bit more and a bit more. So the bottom row is the lower injection rate. And I think that's pretty good. Okay, I'm always suspicious of calculations that agree really well with the experiments, but I would say that's pretty good. This shows the slip, and again, the top number here shows the onset of tertiary creep identified in the experiment. The red is the calculation. The blue is the observation. You'd expect the calculation to be ahead of the experiment because it's a little easier to identify the rapid increase in velocity in the calculation than the experiment. This one is not, so that's an anomaly. But again, I'd say this is pretty decent.
John,
This compares, yes,
John, it's Chris. Sorry to interrupt, but just
no,
want to,
no problem.
I want to comment on like your idea that, yeah, the last thing you want to do is reproduce the experiments too well, because there's plenty of, problems with the experiments. But in your calculations, you don't have a finite permeability, do you? So
No. Actually, I wasn't implying that there were things in the experiment so much as maybe things in the calculation.
yeah, well, it's probably both right now.
But yeah, I forgot to mention that the permeability is high enough here that you can assume it's drain conditions. So the pore pressure at the fault surface is essentially the same in the reservoir.
Mm-hmm. Yeah, okay. Yeah, thanks. Thank you.
And this compares the calculations for the 4 cases. The slower rate occurs later, as you'd expect. And the 80% level also occurs later, and that's consistent with the experiments, although I haven't shown them here. Now, yes, this is the traditional picture of failure under creep conditions. You're increasing the pore pressure, and so the Morse circle moves to the left, and eventually it hits a failure line that's established by another set of experiments. But the interpretation of the rate and state friction calculation is different. Okay, because the shear stress is constant because you're in creep conditions, you're increasing the pore pressure, so the effective normal stress is decreasing. So the friction coefficient must increase. And so that's shown here. You're again moving to the left, but you have an increase of friction coefficient until the velocity gets high enough that you see this unstable behavior. And because this term must be constant, you see a drop in the state variable. So that's shown here. You have this state variable up here, and when the velocity increases rapidly, that must decrease rapidly, which makes sense because the age of contact of the asperities must be going down. One of the things you can do with the calculation is once you have a reasonable agreement with the experiments, you can look at the effect of other parameters, and this looks at the effect of the Linker-Dietrich term. So 0 is no effect of that term. The value of alpha must be below the friction coefficient, which was about 5.5. So that's the highest value. And you can see the effect of that term is to delay the onset of the rapid slip in the first column. In the second column, the little x means that the calculation stops. So MATLAB cannot converge to a solution. And I'm not exactly sure why that is, although we used several of the algorithms, well, all the algorithms in MATLAB. But I think it has to do with the radiation damping term becomes inadequate, that if you really increase that, you can extend the calculation further, but you have to do so to unrealistic values. Let's see, how am I doing on time? Oh, yeah, still some time. Yeah, so the conclusions are here. The calculation agrees pretty well with the onset of tertiary creep. They do reinforce the conclusion of the experiment that even if you have velocity strengthening behavior, pore fluid injection under creep conditions can give you very rapid slip. I said an advantage of this simulation is you can look at other pore pressure increase protocols, and we did do that in the paper. You get a slightly different interpretation of failure in the rate and state formulation. And one of the advantages of the rate and state formulation overall is that the failure is embedded in the solution, that you don't need to make an additional set of experiments or an additional assumption about a failure line. Okay, so this goes on to the second experiment, which is done on the shale, which has considerably different properties than the carbonate gouge. And again, I think I mentioned it, but Marco suggested this experiment and helped out. It's done in the same apparatus, the double direct shear. Most of the parameters can be obtained from the paper. You can see here that B is actually negative. So the Linker-Dietrich effect flips the sign, and B is much less than A, so you have very strong velocity strengthening. Again, we don't know the Linker-Dietrich term, so that was just assumed. Here, the permeability is much lower by 3 orders of magnitude than in a carbonate gouge. So here, the difference between the pore pressure in the reservoir and on the fault surface is going to be significant. We use, again, the value of this delatency coefficient, Siegel and Rice. And I think I mentioned earlier that this is because it's based on that single set of experiments by Chris, for which I'm not suggesting any deficiencies in the experiments, but it was done on quartz gouge. And so I think there's room for additional look at this, the value of this. You'd think that epsilon would depend on the effect of normal stress. However, paper by Samuelson et al. Found that it didn't. So again, that's an issue that I think needs further investigation. Let's see if I said anything Yeah, so I've said all those things. So this is the pore fluid flow. The blue is the reservoir pore pressure, and the red here is the calculated pore pressure using a value of the permeability that's roughly the same as in the experiment. We had to choose it as slightly less to get a reasonable agreement with what they show in the experiment. So they have a plot like this, and if we use their value, well, pore pressure on the fault surface doesn't get to the reservoir value until almost the end of the segment, which is not what is shown in the experiment. And this is the case for the more rapid, well, not the more rapid, but the smaller increments of increase of pore pressure. This shows the calculated velocity in red against the measured in blue. So there's a lot of differences. One thing in this, the 90% shear stress level, you see this spike. Now the paper shows the velocities from the onset of the creep segment. Well, no, it creeps for another hour here, but they show, yeah, the onset of the creep experiment. So you don't know whether there was something like this in the experiment. It's very short duration. Maybe it could have been missed, but it's a big effect. It seems to be due to the very low coefficient of friction, which I also forget to mention. It's 0.28 as opposed to the carbonate gouge, which is about 0.55. It doesn't appear in the 80% level. So, the trend is roughly the same. You don't see, here you see the observed velocity sort of follows the increases in pore pressure. Here at the 80% level, it's pretty hard to see that. Okay, so yeah, I think the data here is a little more variable, not again due to any deficiencies in the experiment, but I think it's due to the character of the material. You do see an increase in velocity at the end of the experiment. It's very small. Before I was plotting the log of the velocity, this is the velocity itself, and you're only up to 1/10 of a millimeter per second. The calculation gets to a value about that, but the rate of increase in the experiment is much higher than in the calculation. So again, that's a discrepancy. Since they're both increasing, you kind of wonder, well, if the experiment had gone on longer, would they get to higher velocities or not? This is pretty low at this extent, so I don't know the answer to that. And maybe because of this rapid upswing, the experiment could not have been continued further. This shows the displacements. They look a little better, but you still have that discrepancy. So some conclusions on this part. Yeah, the calculations, the observations do not really agree that well, particularly in comparison to the carbonate gouge. So I said this, the calculated and observed velocities at the end of the test are similar and small, but the velocity in the experiment is increasing much more rapidly than the calculated. The displacements agree better and do have similar values at the end of the experiment. Yeah, so why is there such discrepancy between the calculations and the experiments? There's lots of reasons you could think of. The very low coefficient of friction, maybe the negative V, very strong velocity strengthening. And in both experiments, the authors looked at microstructural observations, and in both cases, they show an evolution of the microstructure, which I would say is more prominent in the shale. You see evidence of shear localization, fabric formation, anisotropy, and possibly some other things that really aren't in the rate and state framework at all. So those are possible reasons for the discrepancy. Okay, so yeah, we're on to the last segment, which I will probably abbreviate a bit in the interest of time. So these are experiments which have an oscillatory pore pressure oscillation. And this is kind of under construction still, so there's some things a lot of things we need to look at that we haven't. And their main conclusion was that the fault slip behavior is governed by fluid pressurization rate rather than injection pressure. I'll make an aside here that the dependence on the fluid pressurization rate has also been observed in other experiments, which I did not mention, and in some field, not field, but modeling studies. However, you shouldn't interpret that as a departure from the effective stress principle. The effective stress principle says that failure depends only on the pore pressure itself. And that's been a very robust description of what happens in experiments and in the field. And I don't think you can imagine circumstances where there would be a departure from the effective stress principle, but there's really no evidence for that. I'll say why this is not evidence. And no one has suggested, I think, a revision of the effective stress principle. So why does it depend on the pressurization rate? Well, a couple reasons. If the rate is competing with some other rate, and in the rate and state friction experiment, that rate is the critical sliding distance divided by the velocity, then the pressurization rate is going to come into it. So that competition affects the results. In other cases, which are really not well modeled, well, they're not modeled at all by the block model, you can have an inhomogeneity of the pore pressure on the fault surface and have local effective stress failure. But if you look at the difference between the normal stress and the pore pressure in the reservoir, it seems like a departure from the effective stress principle. And a nice experiment on that was done by Passagulo, mispronouncing the name again, Brantu, and one other author that I can't remember. So this experiment was done in axisymmetric compression sample with a saw cut, and this shows the loading program. It's hydrostatically loaded, then the axial stress increases. They get up here, and then they start the pore pressure oscillations, which are shown in the inset. And they're all at a single period. And these are their results, summary of their results. So they looked at two values of the confining stress, and they did experiments at a higher reference rate, but these are only the values, they only show the results for the lower reference rate, and a reservoir, an average pore pressure of 10 megapascal. Okay. So the rows are increasing amplitude of the pore pressure relative to the average rate. the first column is stick slip events. These are aggregated from multiple periods of the experiment. And they occur near the peak. Here it's slightly before, right on the peak. The middle column shows acoustic emissions, which are not really localized for no oscillation. As you get higher magnitudes of oscillation, they again are near the peak, slightly after, slightly before, slightly after. The right side shows the results for the larger confining stress. Here you get, again, well, you don't get any stick slip until you get to the highest oscillation amplitude relative to the average pore pressure. And then you do get stick slip, and you see pretty strong concentration of the acoustic emissions near the peak, again, slightly before. This is at odds with the calculation. The calculations I'm going to show are for this 45 megapascals, and we see really results that are similar to the 30 megapascal. So that's a discrepancy we haven't really resolved at all yet. In the axisymmetric compression case, there's geometric coupling between the normal stress and the shear stress. And I won't go through all this, but this was looked at by Dietrich and Linker, and also Guillaume Chambon and me quite a while ago. One of the results of that is the K critical. This would be for a drained case, constant pore pressure, is greater because of this coupling. So there's this term subtracted in the denominator, which makes it greater than the value, the expression at constant normal stress, and so that is destabilizing. And again, there's also a term that comes into this pore pressure equation, but that's really not relevant in this experiment. Okay, so again, most of the parameters we can get from the experiment. The permeability is high enough that the reservoir pore pressure is about the same as the fault pore pressure. So the diffusion time is much, the period of the oscillation is much greater than diffusion time. So yeah, you get drained behavior. This is all non-dimensional variables, but 100 corresponds to 100 to 5,000 seconds, depending on the particular values of DC and V naught that are used. And just for an example, we've taken the case of K over K critical is a half. When you get to that, when you use that, you see, yeah, that you do get, so this is two cases. Epsilon is the ratio of the oscillation amplitude to the average pore pressure. You do get a rapid increase in the velocity. It's greater for the greater epsilon, as you'd expect. And it occurs a little bit after the peaks here, but only every third peak. Okay, so the paper does not show results for multiple periods of the pore pressure. However, they find that the frictional parameters are not constant, but vary with velocity. So A is about the same, but B and D sub C, well, they're kind of scattered, but they definitely, D sub C decreases and B increases. These are for the two reference velocities, the smaller on the left and the greater on the right. I think I have a short time to make a little digression here, but, yeah, so this really is at odds with standard rate and state friction because the, observation there is that A, B, and D sub C are essentially constant. However, there are some additional, let's see if this is on the next slide. No, let me go back. Yeah, so there are some other formulations. The CNS model, which is the Chen, Niemeyer, and Spears model, which they say is microphysical. It's basically a competition between granular deformation and pressure solution. And they find that you can have dependence of the standard rate and state parameters at certain velocity ranges. There's also a formulation by Sylvain Barbeau. I don't know that one quite so well, but it's based on a power law dependence rather than a logarithmic dependence. So there are some differences here. And again, to continue with this aside, we've used the CNS model to look at some data on the temperature dependence of frictional parameters. And the motivation was some old work by Blampede, which showed that there is a slight change from velocity strengthening to velocity weakening at about 300 degrees. And that turns out to be the temperature at the borehole, at the bottom of the borehole for the Forge site, Frontier Observatory for Research in Geothermal Energy in Utah. And we, meaning mainly Cheng Mei, the postdoc, were able to simulate that using the CNS model with some modification of the parameters. The Barbeau formulation, I think, can also simulate this because it's a multi-mechanism formulation. One other thing I was going to say. Oh, yes. So there's theoretical evidence, mainly due to Jim Rice, that the temperature dependence is 1 over temperature, the temperature dependence of A. But that seems not to agree well with experiments on parameter variation with temperature. But you can include that in the CNS model, again, with some modification, and it occurs in the Barbeau model. And thanks here to Chris and Andre for very helpful discussions, really a tutorial on their model. Okay, so going back, if you include that variation with the velocity and plot, this is a plot of the spring stiffness divided by the critical value. So below 1 is unstable, above stable. And at the higher reference velocity, it's unstable from the beginning. Okay, and paper Noel and all has a plot like this, but it's not, does not have this correction term for the coupling between normal stress and shear stress. Okay, so I talked about that. And so, yeah, you can get things like this. So this is at very low amplitudes of the oscillation relative to the average. You do see spikes, although the increase in velocity is not so large, about 4 times the reference value for the larger amplitude. You do see larger spikes for larger amplitude, and it occurs before the peaks in the pore pressure. Now, actually, the biggest rate of pore pressure occurs between the peak and the trough, so this is closer to the highest rate of pore pressure. So we've done a number of simulations. This is at higher amplitudes. So you get, again, higher spikes, but here it occurs near the trough. And this is the case of the lower pore pressure, which I don't think they show the results. In here, you don't get spikes at all. You get this rolling behavior, and it's very close to the reference velocity. So it's possible they didn't see anything in experiments in this type. Okay, one other thing I'll mention, this is at the higher reference velocity. And for the low pore pressure amplitudes, you see some increase, but again, it's really small. It's only about 20% of the reference velocity. If you increase the amplitude of pore pressure, again, the calculation stops for higher. And again, we think this is due to the inadequacy of the approximation for the inertia, that if you increase that damping value to unrealistic values, you do get a continuation. So I think I'm gonna stop there. And let me go ahead and just go to the conclusion. So yeah, there are some, well, that's probably an overstatement at the beginning here. There are a lot of discrepancies. There's some consistency with the conclusions of Noel. You do find that oscillating pore pressure can promote seismic-like behavior. And the last two statements are consistent with their results, but there's a lot of discrepancies, and we still need to do some additional work on this. Some overall conclusions. I think I've said these already. Yes, so, and still more. I think they're roughly consistent with many features of the experiments. There's other things clearly in the experiments that are not included in rate and state friction. And the big conclusion from the first part of the paper is that, the first part of the talk is that fluid injection and creep experiments are consistent with the observation that rapid, unstable slip events can occur, even though you have velocity strengthening behavior. And yeah, so thanks for listening. I would be happy to entertain any comments, criticisms, questions, or suggestions. So.
Thank you very much, John. Fabulous talk. I'll invite people to unmute, turn on their camera if they want to do something. Join me in thanking John. Yeah, really, really interesting talk. Okay, so yeah, probably the easiest thing to do if you're not used to Zoom, there is a reactions button you can use at the bottom of your screen. Raise your hand. And I'm going to self-raise Paul Siegel's hand, if you don't mind, Paul, because he already put a question into the chat.
Oh, yeah. Paul's here, so okay, he's going to tell me what's wrong with this.
No, not at all, Todd. It was a great talk. I'm just wondering, you talked in the beginning about the fact that we don't really have great constraints on high latency constitutive laws or parameters, and you didn't say much about that. And I'm wondering whether the experiments constrain high latency effects in any way. I guess that's the main question. Whether you looked at that.
No, we didn't really look at that. I mean, we use your and Jim's formulation. So yeah, that I think would be something to look at, whether, well, it doesn't come in the experiments that were drained.
Sure.
Right, because, and so it was only the shale experiments where there is a difference between the reservoir pore pressure and the fault pore pressure. And I'm a little hesitant to pursue the effects of different values of that with the shale experiments, because the agreement was kind of not so great there. And the shale experiments, I think, are a little bit anomalous, not anomalous, but they're more complicated. They don't track the pore pressure increases quite so well. So, yeah, that's a good suggestion, though. I think.
I guess the question is, were there measurements that would help constrain that you didn't mention?
Well, I don't know of any.
Sometimes they measure the fault normal displacement that would help.
Ah, okay. Well, I think that's what Chris did in the original experiments, but I don't know of any additional ones. Maybe Samuelson in his paper did, but they found that the Siegel-Rice formulation explained their observations too. So, I mean, that's why I said I think there's room for more experiments in this area.
Definitely. Thanks, John.
Yeah, good point. And before I turn things over to Nicholas Brown too, I'll just say that, yeah, there have been some, including by others. But I guess John, the point I take away from what John's saying is that there's room for, really understanding how much that parameter can vary for different materials and under different conditions. There's some measurements. It's not like they're only ones exist from 1990, but there aren't that many. Nicholas Brown, too, please go ahead.
Hey, John.
Hi, Nicholas.
I have two questions. I mean, one first question is very along the same lines as what Paul Segal just mentioned, is the latency effects, especially the values that typically people measure in these experiments, is very small. It's like epsilon is 10⁻⁴. And it's 10⁻⁴ times the ratio, the log of the ratio of V. So this, I mean, porosity is pretty much nearly constant. I mean, in these things, you have to have a huge change of speeds to really see a substantial effect in pore pressure and so on. So I'm just curious to see whether this, makes any difference to your thing, but I guess it's part of the same question. In terms of measuring dilatancy, in these experiments, the problem is that you lose gauge. I mean, I think Chris can confirm, right? Every time you slide things in a finite block, you're going to lose things out on the edge, right? And typically if my memory is correct, Chris, and again, you can correct me, what you do is you have a long-term trend for the thickness, and you look at small variations around that long-term trend. But that long-term trend is clearly compaction, if my memory serves me right? And so have you looked at incorporating any of the slip dependence, direct slip dependence? Because this is it's not like rate dependent, but like something like a geometrical thinning or thickening, depending on the situation, where you would have maybe a larger effect, but not depending directly on rate.
Well, yeah, those are two good suggestions. To the first one, I would reply that, yeah, you do get big velocity changes. And I don't think that term is always negligible. In the simulations we did, I forget which ones, the ones we compared with the Kilgore experiments, yeah, the change is significant. And I think it's, because you are getting very high velocity changes. The second point is, I didn't emphasize this enough, but the assumption of rate and state friction is that you're basically starting from steady state. It does depend only on the velocity, whereas, the experiments do show a strong slip dependence. So I think, that a better model would be some combination of slip dependence with rate and state friction, particularly not only in experiments, but when you're thinking about mature faults. So they're basically stuck for a long time, and then probably you've got to slide them to get things going, and then you might rate and state friction might kick in. So I think that's an important point.
Nicholas, you want to follow up?
Well, I mean, I think I agree with the thing. I mean, I had maybe another question, but for a different point. If there's no other questions I can ask, but
Well, then let me just say, if you're gonna go to something slightly different, yeah, you're right. A lot of the experiments show long-term trends. But they basically agree, normally sort of, your experiments too, you basically agree with, reaching, a kind of a steady state, a critical state, soil mechanics type critical state, right? Where you've reached a kind of steady state porosity. That doesn't mean that we don't, but in double direct shear, you often do see long-term displacement thinning that occurs that's on top of the critical state being or reaching a critical, constant porosity. But
Yeah.
anyway,
No,
agree.
I mean, again, following up from this, I agree completely. You would hope, everything else being constant, you get some kind of porosity, critical state porosity. But in nature, I mean, that's for the experiments. But in nature, if you have like 1,000 years in between events, or even 100 years, it's very likely that the rock is not going to look the same, and it's going to be like a different rock now. You have to, it's like there's another state variable. That's what I mean. There's another state that changes in the meantime that might change that. But again, I'm not sure we know so much about this.
Yeah, I should just correct something I said. I said mature faults, but I meant dormant faults. That's what happens when you get to be my age. You get these senior moments that drop in.
Okay, great points. Now, before I turn things over to Massimo Coco and Garrett Drazen, I really want to encourage, especially young people, early career scientists, join the conversation, raise your hand. In fact, if you raise your hand fast enough, you can go before somebody like Garrett Drazen. He won't mind. Don't worry.
No.
Massimo, please go ahead.
Hi, John. Excellent,
Massimo.
excellent talk. Thanks. I have two questions. One concern, you mentioned in your presentation the shear fabric evolution. So
Yes.
the question is, if we have evidence of shear fabric evolution, it could be even possible that the gauge, for instance, does not reach any steady state. So how, in this case, can we still apply right state in a critical circle approach? And the second question concerns the dependence of the A and B, the right state parameters on velocity, because this might have huge also implication of the critical stiffness. And I would like to better understand, because it seems to me that when you allowed the B and A to change, your critical stiffness was somehow constrained. Could you clarify this?
Yeah, well, those are two good questions. I mean, let me see. So the first one was the evolution of the gouge. Yeah, I mean, I think that's an issue, and the experiments of Scuderi, they do look at the microstructure, and there is an evolving fabric of the gouge with shear localization and cracking. So yeah, that's not in the rate and state formulation at all. And I guess I'm not really sure how one would put that in. In the for your second question, yeah, it does change the critical stiffness that in the, let's see, I don't know if I can go back to this. Well, I won't go back. So I showed a slide of the critical stiffness against velocity. And in the original, the slide that's in the paper by Noel et al., they did not make this. They also showed a change from stable to unstable. But when you include that normal stress term, the higher velocity is completely unstable. So yes, I agree with you that that's going to change the critical stiffness. But again, I don't know how to do that yet. So yeah, that's an issue. I mean, there are a lot of issues, I think. That I didn't really answer your question, but that's the best I can do, I think.
Yeah, no, thanks. Because actually, in some experiments that we did with Giacomo Pozzi on dry samples, not with fluids, but in any case, for serpentinite, for instance, the possibility of having this lack of steady state, because you have a double response of the gauge, could require, for instance, the possibility to add a second state variable, similar to what Nicolas just suggested before. But if we increase the number of the state variable, our analysis of stability changes, and more important, we have the effect that the small perturbation of the evolution equation might have huge implications on the governing and the stability definition. So moving to 2 or 3 state variable, it is farther than, of course, normal stress changes would complicate a lot the dynamics. So I agree with you.
Yeah, those are all good points. I mean, I started with the simplest model I could think of and work out. So, yeah, those are all good points.
Continuing to encourage everyone to raise their hand and participate in the discussion. And thank you, Georg.
John, thank you very much for the nice presentation. I have one question. So you showed the nice experiments that Marco did with the shales. And, you know, you get the impression that towards the end of these experiments, the material also started to transfer into, you know, some accelerated tertiary creep, which
Yeah.
the model didn't capture. You
That's
captured
right.
it for the carbonates, but not for the shale. So
That's
what do you
right.
think is the main reason for that?
I think it's the very strong velocity strengthening.
Okay.
So you just don't get that rapid increase, at least during the at least predicted during the duration of the experiments. The velocity strengthening is very strong there. And even when you get that rapid turnip, the velocity is not so high. You know, the question you pose is a good one, but if you did the experiment longer, would the calculation be even more obviously in disagreement with the, and, you know, I guess in that case, I'm a little less, I mean, I think Rate and State does a pretty good job with the carbonate, but with the shale, I'm not so sure. I think there are a lot of other issues going on there that are not captured by Rate and State.
Mm-hmm. Thank you.
Yeah, that's a really good point, because it's, you know, the simplest interpretation, if you have velocity strengthening, like John's saying, then you don't even expect accelerating creep, right? As soon as
Right.
it should die. So there must be something else going on. Yeah. You know, John, you were reticent to, but I think it's not very hard to share your slides and also see us if you just share part of your screen or share your screen without going into presentation mode.
Okay.
Because I would like to ask a question, not seeing any of the hands, about the kind of critical time that's associated when you were doing the modeling of Corentin-Noel's experiments, and you have an oscillating pore pressure. You saw some discrepancies, and I just wondered, you know, if you thought about that in terms of the kind of the critical time associated with slipping a characteristic distance d sub c, right? You know, like if you
Yeah, I mean, let's see,
we can see your screen, John. Can you see us a little bit too?
yeah, I don't see you anymore, but
Okay.
well, I'll talk anyway. So, yeah, one of the things is their experiments were always done at a single period. And so we
Right.
did our calculations at a single period. But it would be interesting to address your question by looking at different periods of oscillation. And so that would be relative to the time scale of friction, which would be d sub c over the reference velocity. So yeah, that's a good suggestion, but we haven't gotten to that point yet.
Yeah, because it does suggest some delays and some kind of offsets, as you say, between the pressurization and the response.
Yeah.
Yeah, even
that's something we need to look at and actually had planned to look at, but we just haven't gotten there yet.
Yeah, okay. Other questions? And John, if you bring that bar back that you put away at the beginning, it will allow you to see at least a few people or the
Oh,
person.
I can see now. I realized what I needed to
Yeah,
do there,
I see,
so.
I see, yeah. Other questions? Comments? Georg, go ahead.
Yeah, John, so let's speculate. Why do you think in this extremely velocity strengthening material you observe this transitioning into accelerated tertiary creep? What do you think? What would be your take on what's happening there? Because we've done socket experiments on Monterey material, and we see similar things. And
Yeah. Well, it's clearly the effect of the pore pressure. That the increase in pore pressure, it destabilizes. Well, it destabilizes due to the decrease in the effective normal stress. But the shear stress is the product of that times the friction coefficient. And in these experiments, the shear stress is constant. So if you have that decrease in the effective normal stress, you must have the friction coefficient increase, and it does that by increasing its velocity. But
Okay.
your experiments are not creep experiments, are they? Or?
No, these were not creep experiments. These were relaxation tests.
A relaxation test.
So we injected so the sandstone experiments that were relaxation tests. So we fixed the piston and then injected the fluid. And for the shales, these were displacement controlled experiments.
And you do get.
And there was no fluid. There was no fluid involved. But what
No
we
fluid
found
involved,
was what we found by placing strain gauges around the fold. We saw that a slow pulse was going through the interface. So as if, a slow rupture would propagate through the interface.
Okay.
So, my suspicion would be that when you creep, you still accumulate stored elastic energy. And at some point it becomes so large that it accelerates into tertiary creep.
Yeah, that could be. So you think it's a inhomogeneity along the
Yes.
frictional surface that, yeah.
Yeah.
Again, that's not in the.
Yeah, sure.
model. You know,
Yeah, sure.
I mean, in Nicholas' experiments on injection, yeah, it is that inhomogeneity along the frictional surface that drives the instability. It depends on the injection rate. So yeah, that's an important that's an important consideration in the experiments, that the spring block model is really not a good model for those kinds of experiments where you are able to detect inhomogeneity along the frictional surface.
Thanks again.
Other points people would like to?
Chris, can I comment on this that Georg and John were discussing? Because when we did some experiments with fluids, taking the gauge from the Pedretto gauge from the target fault in the Pedretto tunnel, we found that the tertiary creeping started when we reached actually the level of the static Coulomb friction. So dilatancy started much before, which followed by primary creep essentially. But when the pressurization allowed the friction to reach the nominal value of static friction of 0.49, 53, I don't remember, that was the time in which for fluid pressurization creeping starts. So this could be possible, the same that Georg was just suggesting, that while creeping was accelerating, it was still storing some elastic energy as well. Because it is a process in different stages that require time, and is not a instantaneous full dissipation.
Yeah, those are good points that, yeah, you need to go to a more, a better model of slip in the experiments to address those, which we should.
I will send you the paper by Volpe with Marco. We did with the Giacomo Pozzi, Marco and Cristiano, by the way.
Yeah, that'd be great. That'd be great.
And speaking about experiments, I see Corentin Noel's camera on a few minutes ago, at least. I don't know if he's still here, but you know, Corentin, did you listen to the
Yes.
questions about whether you looked at different oscillation periods too, or thought about that in those
Yes.
experiments?
Can you hear me? Yeah.
Yes.
So we didn't. So in the experiment, we didn't try different oscillation periods because what we tried on other samples, but what we saw is that it just depends also on the. So we're constantly loading our sample. So it's the ratio between the oscillation period and how fast you load your sample that matters. So we chose to fix one and the other to arrange the thing. I don't know if it's very clear, but
So even when you had the different reference velocities, you didn't see an effect of, well, I'm thinking of the ratio of the reference velocity to the period of oscillation.
So yeah, so we changed the reference velocity with no oscillations. Like if we kept constant the pore pressure, we tried also to change the background velocity to see what happened also.
Yeah.
In that case, it does change for both cases, for both different confining pressure. Increasing the background velocity was turning the system from stable to unstable sliding.
Okay. Well, I may get back to you if we try more simulations to see if, yeah, to get your comments on that.
Yeah.
Yeah, Corentin, right? Those are complicated experiments, hard to change too many things at once and still keep track of and still produce a nice data set. Other comments or input? Well, if not, let's, yeah, please unmute, turn your camera on if you'd like, and join me in thanking John for really a fabulous talk and a great discussion. Thank you very much, John.
Thank you, John. Thank you.
Yeah, thanks for all the questions and suggestions. It's I'm on phased retirement right now, but I clearly have a lot more work to do before full retirement.
Okay, ciao.
Yep.
Just a
Ciao,
question,
John.
what
Thank
you
you
say
very
now,
much.
right, John?
Okay. Yeah.
Thanks, everyone.
John, thank you very much.
Bye bye.
Bye-bye.